generalized localization principle was introduced by Ilin in 1968. So we have recently obtained the following results in these two papers where we solved problem of generalized localization. And I would like just to talk today about this result. But first, I want to give some short survey on convergence almost everywhere of one-dimensional, then multidimensional Fourier series, and then indicate a sketch of the proof of the above result. So first of all, what is this generalized localization principle means? So Lusin's conjecture says that if function belongs to L2, then Fourier series converge almost everywhere. But localization principle will simply add one more condition. Let f belongs to L2 and equal to 0 in some open set omega. And then we will investigate convergence of Fourier series inside this omega set where function is 0. Now, this problem of expanding any function on trigonometric series arise in mathematical physics, and this is investigation of this problem is very important. Even nowadays, we can see a lot of papers on differential equations, partial differential equations, even fractional partial equations, where they use this trigonometric Fourier series. So this is partial sums of this Fourier series. And then when we want to go to multidimensional case, it is convenient to rewrite these partial sums in the form of 1. Here, CK is defined here. And with this formula, we can just easily go to n-dimensional case. So Lusin's conjecture, that was in his dissertation, Integrals and Trigonometric Series, in 1915, he made conjecture that Fourier series of any function from L2 converges almost everywhere. In other words, if you have this number series which converge, then this functional series converge almost everywhere. This was conjecture of Lusin. So over a period of many years, Lusin's conjecture attracts attention of many specialists, like such as Kolmogorov, Bari, Menshov, Stein, and many others. But in 1922, Kolmogorov constructed a remarkable example of function from L1, whose Fourier series diverged almost everywhere, even at any point of T1. So after this result, well, specialists think that once you have divergence in L1, why not in L2? That's why many specialists try to construct counterexample for Lusin's conjecture. After defending dissertation, Lusin, he was a student of Lebev. Lusin returned back to Moscow University, and he led a seminar, theory of functions. And after him, this seminar was headed by Menshov and Ulyanov. Menshov was a direct student of Lusin, and Ulyanov was almost his student because he was a student of Bari. So almost every seminar included in one sense or another the Lusin conjecture. At all conferences on that time on theory functions, problem and subsequent work to Lusin's conjecture come up. Therefore, since Lusin was justly considered the founder of the entire Soviet mathematical school of theory functions, almost entire Soviet school of theory of functions knew perfectly well everything about this problem. I'm not saying that everyone wanted to prove this problem, but everyone in this area, they know what is happening around this problem. So this long story was closed in 1966. So that means after 50 years, more than 50 years, by Carlson, who later received the Abel Prize, he published remarkable result. Actually, he proved that losing conjecture has positive solution. And in many seminars of Moscow State University, Carlson's proof was discussed. The proof really is very complicated. It is almost 60 pages. And now there are many different interpretations of this proof. In particular, Pfefferman also gave his version of, this is also paper about 60 pages. And this work consists of 6 chapters. And the first 5 chapters are very easy to understand. But chapter 6, more difficult as far as for me, it's more difficult to understand than Carlson's original proof. And interestingly, at the end of this article, Pfefferman wrote, "Don't worry if you don't understand chapter 6. So I want to emphasize, especially emphasize that in seminar of Levitan, a report on the proof of Carlson's theorem was made by Alimov. On that time, he was a student of Faculty of Physics. It may be worth mentioning that even Carlson started by trying to find continuous counterexample to Lusin's conjecture, making use of Blaschke products. And main thing, Zygmunt was very, very positive about that. But after some time, he realized eventually that his approach couldn't work. Only after this, he tried instead to prove Lusin's conjecture. And this information I have taken from this interview. You know, this Kolmogorov's example, it is function from L1, but it is unbounded function. But when you see this construction of Kolmogorov, you think that you can little bit change this function and it will become continuous. But in fact, it's not like that. So Carlson's result has been improved by Hunt. This is a German mathematician in 1968. That means after 2 years, who proved the same conjecture, same result for LP functions, where P is greater than 1. So that's the problem in classes LP. Convergence almost everywhere is completely solved. If P is greater than 1, then we have convergence almost everywhere. If P equal to 1, then we have Kolmogorov example. Right, now multi-dimensional case. Let's consider this multi-dimensional Fourier series. In multi-dimensional case, we have great variety of natural partial sums. So we'll consider only 3 of these partial sums. First, so-called square partial sums. So we take n1 less than k, etc., and this n, remember, vector. So n less than k. So we say that this series converges over squares if this limit exists. Okay, now see, what we do is we first take these numbers here, these numbers from here, we take summation, and then we go to next k, bigger, and inside this bigger square, and then k tends to infinity. You see, in this case, this previous set consists on the next set. Now, okay. Okay, now this way. Now rectangular partial sums. Can you hear me? I'm sorry. Alabere?
Yes.
Okay. Okay, I'm sorry. So rectangular partial sums. This n1 is less than k, and here L, so that means different numbers. And we say that series converges over rectangles when minimum of these tends to infinity. So here you see this, we first take like this rectangular, and next one can be like this. In this partial sums, the previous set doesn't include inside next set. Okay. Now, the last one, spherical partial sums. So we take here ball. First, we take summation on the ball, then lambda tends to infinity. Here, so take ball with radius lambda 1, and then lambda 2, etc. Lambda goes to infinity. So with these three partial sums, you can write in this way, and where this omega is some finite subset of Zn. And you see, you can note that spherical and square partial sums, when you consider these partial sums subsets, form a family of enclosing sets. Whereas when you consider rectangular partial sums, this omega, omega is not enclosing family of sets. Now, eigenfunction expansions. So all these partial sums are natural generalization of this one-dimensional case. But from spectral theory point of view, natural generalization is spherical partial sums. When you consider periodical Laplace operator, it has these eigenfunctions and these eigenvalues, and eigenfunction expansions corresponding eigenfunction expansions has the form. So that means you have spherical partial sums. That's why spherical partial sums is more important for application point of view. Now we will consider Lusin's conjecture in multidimensional case. First, we consider square partial sums. In 1970, just after 2 years of Hunt's result, Tizadze extended Carlson's theorem for n-fold Fourier series. So, in fact, this results in L2, that if function is from L2, then square partial sums converge almost everywhere. But this proof you cannot apply for LP functions. For LP functions, Schurling proved in 1974 the following result. Any function from L1, LP, P greater than 3, has Fourier series which converges to F when you consider square partial sums. So, along with Kolmogorov's example, this chapter is closed. That means if you have function from LP, P greater than 1, then you have convergence. But if this is P is equal to 1, then you can apply this Kolmogorov function and you get counterexample. You can take this as Kolmogorov example, and F2 is arbitrary function from L1, and it's not difficult to see that this function has Fourier series which diverge almost everywhere. So rectangular. You remember this partial sums, the sets here not enclosed. That's why here very strange result. This was proved by Pfefferman. So there is this function, continuous function, which has Fourier series divergent almost everywhere T2. So for rectangular partial sums, also this chapter is closed because for any P in LP we have divergence. That means there is no convergence almost everywhere. Now spherical partial sums. Many mathematicians tried to prove Carlson's result for spherical partial sums. Carlson himself, Stein, Pfefferman, and many others, but unsuccessful. So, but for these partial sums, we can prove the generalized localization principle. Now, this will be our main result. So in this connection, we note that in this survey paper, which was published in 1976, it was formulated the following problem. Does generalizing localization hold for the spherical partial sums on L2 T square? That means at least for double Fourier series. So this problem is called the problem of generalized localization for spherical partial sums. So this is a definition which was given by Ilyin. So we say that for the S lambda, there is generalized localization principle if f belongs to L for any function from here, which is 0 on open set. We have convergence almost everywhere on omega. So if here you take not almost everywhere on omega, then we will have a Riemann localization principle. And this generalized localization principle here almost everywhere. Now, by definition of Fourier coefficients, these partial sums can be written as convolution like here, and then this is kernel of this integral operator. So we noted above that generalized localization principle is easier to study than convergence almost everywhere. Natural question is why? The thing is that when you want to investigate convergence of Fourier series, you must investigate this asymptotical behavior of this function. And then you can see that the worst estimate for this, it is on the diagonal, x equal to y. If x equal to y, here you have 1, and then this sum is just like constant multiplied lambda in power n over 2. So if x not equal to y, then here you have oscillation and this estimate will be better. But when we study localization, x lies outside of support. Here x is outside of support, but y is naturally on the support. That means x is not equal to y. So here the figure. So we let function is equal to 0 is this open set. So we want to investigate convergence here, and then x is here, and y is in support of f. That's why x not equal to y. So now, when we recall, this is the kernel of integral of this summation operator, and to investigate asymptotics of these functions, you can see it's not easy thing. But if you put instead of this integral, then this integral you can calculate exactly. It is through Bessel functions. You can have this formula. But on the other hand, this is kernel of multiple Fourier integrals. So that's why to investigate multiple Fourier integrals and also generalized localization, it's much easy because you have explicit form of kernel. So generalized localization for multiple Fourier integrals was investigated from 1983 to 2016 by Schörling, Carberry, Terence Tao, Soria, and others. And in the remarkable paper here by Carberry and Soria, it was proved the following result. So in LP, when P is in between, there is localization. So that means if F belongs to this and P here, F0 on the set, then you have convergence to 0 almost everywhere on omega. The thing is that if P is greater than this number, this problem of generalized localization, it's open for multiple Fourier integrals. But if P is less than this, then there is a result of Bastis, which says that here there is no localization principle. So this result, in fact, on eigenfunction expansions of the Laplace operator, in particular for Fourier integrals and also for Fourier series. This is our main result. So if let F belongs to L2 and it's 0 on omega, then we have this convergence almost everywhere on omega. On omega, you remember this function is 0. So that's the problem of generalized solution. Localization for S lambda is completely solved in class LP when P is greater than or equal to 1. That means if P is greater than 2 or equal, then function from here, it belongs also to L2, then we have generalized localization. But if P is less than 2, then the localization fails. This is due to Basti's previous result. So this is our main result. Okay. Now, in the study of convergence almost everywhere, it's convenient to introduce this maximum operator. So it's by this following formula. So our main theorem is based, proof of this theorem is based on the following theorem. Let F belongs to L2 and F is 0 on this ball, and then for any R less than this radius, there is constant such that we have the following estimate. So what means this estimate 2? Estimate 2. It means the following. If this norm is very small, then this integral also very small. And that means the set, the measure of the set where this quantity is big, the measure of that set is very small. So in the course of talk, I will list several essential points of the proof. And this is the first essential point. So instead of omega, we take here a ball. Of course, when you have here omega, then to prove such estimate is very difficult. But this theorem is enough, sufficient to prove the main theorem. So from this theorem, we have the following corollary. If F satisfies the condition of theorem, then we have convergence almost everywhere in this smaller ball. So this radius is smaller than this. So we can prove this. It's not difficult to prove. Once this set is dense in L2, this function we can write as F1 plus F2, where F1 is very good and F2 has very small norm. And then for arbitrary epsilon, we can choose lambda such that this will be small, because here we have convergence of Fourier series, and this measure will be very small. This is because of inequality. This follows from estimate 2, that is from theorem 6. So therefore, if lambda is bigger than this, on this domain, this quantity is less than epsilon. This is because of this epsilon less than epsilon and a half. And this is because outside this measure, this quantity is very small. So this means, so this tends to 0 almost everywhere on BR. So main theorem follows from this corollary. It's not difficult to understand. Let F belongs to L2 and 0 on omega. We extend this function outside Tn to pi periodically, and then we must prove the following equality. So that means if we take arbitrary x0 from this omega, then it's sufficient to prove on this ball we have this convergence. So therefore, we may suppose that F is supported outside this ball, or we can do this translation in variance, and then F supported outside this domain and prove this. But this is in fact corollary to corollary 1. So that's why it is enough to prove theorem 6. Now we go to prove theorem 6. So suppose that F0 on this ball and R is less than this. So now we denote this kernel. Usually you see here in this domain, they take this set usually, because if you take square root from both sides and the square root lambda, we again denote by lambdas and nothing will change. But the main point in our proof, we put square here, square. And this is our second essential point, because when we take here, we must estimate this supremum here and then integrate. This is, in fact, theorem 6. But what we do is, if you take like this, then lambda will be only natural numbers, and this support supremum we estimate with summation. So main problem here, that was main problem in Carlisson's proof also, how to estimate this supremum inside the integral. If it was outside, it's okay, no problem, but it is inside. So what we do is this supremum we change with this summation. Now, and next point is, let's consider the following function, infinitely differentiable function, which is 0 here and 1 here, outside is just infinitely differentiable. And we define function psi by this formula. And outside Tn, we put this function as 2 pi periodically function. So now the third essential point is that instead of theta, we take this function. This is defined here. So in fact, psi has the following graph. So here 0, outside 1. So you see, when we consider this as lambda, in fact, instead of Tn, you can put x minus y greater than r means, so intersection these two sets, because you know, here when we consider convergence on BR, this is smaller ball, and x is here and y is in support. That means x minus y is greater than r minus r small. That's why we can put here like this, but this function here in this domain, it is 1, equal to 1. That's why we can put here this function, and that's why instead of this function, we consider this omega lambda. So to prove estimate 2, it's sufficient to prove this estimate. Now, we need some estimates for Fourier coefficients of this function. And Fourier coefficients we denote by theta gn. And for these numbers, we have the following estimate. Now, this is one of main lemmas. So this function equal to this, and this you can rewrite in this form. And now we should take Fourier coefficient of this function to get this estimate. So Fourier coefficients of this function, you just take integral, and then this equal to this Fourier coefficients of this function of psi, and then instead of this, we can just define n minus m by m, and you can rewrite this as following. Now, let's estimate this sum here. And this is less than this. And now the main point is here. You see, here we are taking summation inside the ball. just let's go here. So n is here, and we are getting summation in this ball, n minus m less than this. So instead of this ball, we can consider another set. You see, this is n, and radius is square root of g. So this radius here is n minus g. Here, remember, n bigger than this. So we can take some, instead of this summation, we can take summation outside of this ball, everywhere here, everywhere. So that will be bigger than this. So what I was going to explain, instead of this summation, we can take this summation outside this smaller ball. So this positive numbers, so this will be bigger. So, and this function, infinitely differentiable function, periodical, that's why Fourier coefficients we can estimate like this for any k here, and only constant will depend on this k, and then this summation easily to estimate this way. So we have proved the lemma in this case. Now, how about this case? Then you see this sum is equal to psi 0. Psi 0 is 0. So that means this sum you can rewrite like sum of two like these sums. That means this sum is equal to this with minus. So we want to estimate this sum, and we go to the next one with minus sign. So that means we must estimate this sum here. Well, and again, you see n minus m is greater than g. Here, remember that n is less than this. So what is happening here? We have summation over this ball, big ball. So where n minus m is less than here, you see, well, here outside. So outside n minus m is bigger than g. So we must take summation outside this big ball. But we take another ball with radius g square root g minus n. And we take this smaller ball, and instead of taking the summation outside of big ball, we can take outside smaller ball. That's why we change this summation into this summation. And we have the following estimate, and just take summation, and we have this. So that's why this lemma is proved. Now, I told that this is third essential point. Why we change this function to this function? Here the thing is following. So this function has the following form, and Fourier coefficients of this function can be calculated like this. Oh, from here it's very easy. So, but we need estimation when g tends to infinity. This function, you see, when g tends to infinity, it's constant. Whereas this function has the following estimate. So when g tends to infinity, this is much better estimate. Now we introduce the following difference between g plus 1g. And for this, we have the following formula. And if this Diophant equation doesn't have solution, then we put 0 instead of this. Well, now for this bigger theta, we have the following estimate. This can be proved just using the same argument as above. I will not stop in about the proof of this estimate. From this estimate, we can, this is in fact this small sum, and when you take summation from k0 to infinity, this, and then you get constant. So we have the following corollary from that estimate. Now, this is the main lemma in our proof, and this is very complicated to present here the proof of this lemma. I will present here without the proof. What's the meaning of this lemma? You see this, when you consider this sum, you can consider like P, let's denote this set G, for which square root in between K and K plus 1 denote this by QK. So G, such G, which you can represent in the following form, and P changes from 0 to 2K. So this sum you can rewrite like this, or otherwise P inside QK in this domain. So lemma 8 says the following estimate. But this estimate is for us not enough. So what we do is, if you here the summation is taking on positive numbers, and we can change the order summation, and we found such a changing of this summation so that you can this sum rewrite in the following form. Here you see you multiply for this, so we can prove that this, if you even multiply to this, you have same estimate. So this is about this lemma. So we proved that there exists such sets and of integers such that the summation gives this QK, and then the set has at most this number of parameters pair, and for some we have the estimate 9. So if we prove this, then here you see this, in fact, I can explain the idea. You see here, the main thing is that if K is 10 and K plus 1 is 11, so this is N. And you see, when you go to M0, M1, M2, here, some spheres here. And this distance should increase when we go from M1 to M2, M3, etc. But it is not happening in this sum here. That's why we change the order so that take some groups of these spheres here, that is this. And then this distance will increase. So this is complicated part of the proof. But if we have lemma 9, then we have the following estimate. Now, so this lemma 5 for small zeta is theta such estimation. And from this estimate, we can obtain the following estimate. So this is proof. It is not difficult. I mean, you put instead of this estimate, and this numbers comes here, and we know how many parameters here, this maximum, this number parameter, put here this number, and this is here, and this you can estimate by constant, and then you have this series conversions. So this is bounded by number C. Okay, now proof of main theorem. So we must prove the following estimate. This is the main estimate. How we can prove? So we introduce the following functions, and with these functions we can write the following equality, because this J plus 1 is equal, in fact, theta big and theta small plus theta small, and put it here, then we get this number here. And the Fourier coefficients of this we denoted by this above. So now, if we consider this sequence of numbers here, such that f0 is 0, so for this we can write the following equality. Otherwise, we can rewrite this equality in this form. And now put instead of FQ this theta convolution with F. And then this FG1 minus FG is theta big, and G plus G FG from this you put here like this. And then for this convolution, we have the following. Now we should take, to prove this estimate, we should take from both sides supremum, right? So we put here sub, and then instead of this sum, because this all positive numbers, we put infinite. So we have the following. Okay, we here multiplied q plus 1 and divide for the same number. And now take integration, and then you see you have the following estimate. Now we have already in lemmas estimated this is less than constant, and this also less than constant, and this also less than constant. That means everything here is less than the L2 norm of fx. So this is a proof of lemma 6, and then from lemma 6 to theorem 6, and we already showed that from theorem 6 we can obtain the main theorem. Thank you for your attention. Maybe not everything understandable, but I tried to simplify the proof. Thank you very much.